Good morning, my dear students. Now we are going to discuss about Hall effect, Hall coefficient, and applications of Hall effect. What is the Hall effect? Whenever a slab of semiconductor is taken and apply the electric field in one direction and in opposite direction of the applied electric field, if you apply the magnetic field, there is a induce of voltage or electric field in opposite to the applied electric field. That means, see here, this is the applied electric field, this is the applied magnetic field. So there is an induce of voltage in this direction, which is perpendicular to both applied electric field and the magnetic field. This induced voltage we will call it as a Hall voltage, and this effect is called Hall effect, and this field you can call it as a Hall electric field. Okay, here I have given a small animation, okay, to understand. Suppose if you take a battery and you apply the current to a rectangular slab, and the electric field is moving in this direction and reaches to another electrode through this wire. Whenever you apply the magnetic field perpendicular to this applied electric field, there is a deflection of these electrons, okay, due to this applied magnetic field, gives the induce of the voltage in this direction. The same thing you can understand in a better way. So whenever you apply the magnetic field perpendicular to the applied electric field into the slab, in the slab perpendicular to the applied magnetic field and electric field, there is induce of a voltage due to the separation or deflection of the electrons and holes in direction of opposite to the applied electric and magnetic field. This is called Hall effect. So what is happening in the Hall effect? If you see here, suppose I have taken this semiconductor slab and we apply the electric field in X direction, magnetic field in Y direction, and we observe that there is induce of electric field in Z direction. The force due to this electric field induced on the electric charges, electron or holes, is called a Lorentz force. Okay, so now for understanding, suppose we apply the current density Jx in X direction is equal to NeV, standard formula, and whenever you apply the magnetic field, that electric charges will be deflected, so I will call it as a deflecting force. Nothing but applied magnetic field gives the deflection force on the charges. Fv is equal to by Ev. So we know that this induced voltage also gives the force on the charges, is called Lorentz force. Fl is equal to EH. At an equilibrium condition, okay, we know that this applied deflection force should be equal to the Lorentz force on the deflected charges. Therefore, EH is equal to B by EV, or EH is equal to B by V, where V is the drift velocity of the electron due to the applied current. Okay, we know that V is equal to Jx by Nv. By substituting this, we will get EH is equal to Jx B by Ne. Here actually it is a cross product, Jx cross By. Suppose these two are vectors, the cross product of this vector should be perpendicular to the Jx vector and the By vectors. Therefore, this induced electric field is always perpendicular to the applied current and the applied magnetic field. We know that EH is equal to VH by T, this is the thickness of the sample, and Jx is equal to Ix by area. Area is nothing but B into T, breadth into thickness. Therefore, we can write VH is equal to Ix by NEB. By substituting this value in this equation, we will get this equation. where VH is, we can write RH Ix By by B, where RH is nothing but Hall coefficient. Therefore, Hall coefficient we can write it as RH is equal to 1 by Ne is equal to BHB by Ix By. So this is the Hall coefficient, a constant for a particular material, indicates the how much Hall effect is there in that material. What are the difference between the p-type and n-type semiconductor? If you see Hall coefficient, in case of p-type semiconductor, it is a positive quantity and gives 1 by Pe. In case of n-type semiconductor, it is a negative quantity, minus 1 by Ne. So this polarity gives the what type of semiconductor. And we can also find the carrier concentration of electrons or holes if you know the Hall coefficient of that material. This is the important application of the Hall effect experiment. So we already know what is the Hall effect experiment. Here there is a digital Hall effect setup. This is a constant current source. We are applying to these coils, electromagnets, induce the electric field, and we have taken a material, semiconductor material, and we apply the constant current source, okay, voltage, okay, through this, and there is a Gauss meter for finding what is the field at this point. By placing this semiconductor material and applying the magnetic field in one direction, electric field another direction, there is the induce of voltage along the z direction. Okay, therefore VH is equal to RH By by B Ix. This is the fundamental formula. From this is a constant value, but whenever you vary the applied current, then we observe the increase of the voltage, Hall voltage. So this looks like a y equal to mx plus c, where m is the slope and it is a linear equation. This is also a linear equation having the slope of Rs By by B if you draw the graph between these two. So here we have given the graph, applied current Ix and measured voltage, Hall voltage Vh. This slope is nothing but RH By by E from this equation. Therefore, we can find the RH value if you know the slope of the graph. Rx Hall coefficient is equal to Bm by By. If you know the RH value, we can find the different parameters that we can take it as application of the Hall effect. We can find whether the given semiconductor is positive or negative, or it has the positive carriers or negative carriers, and we can also find the carrier concentration of the n-type semiconductor and p-type semiconductors. That means n value and p value. We can also find the mobility of the electron or hole, and we can also find the, okay, if you know the VH, we can find what is the applied magnetic field. Okay, so the another important application is this also you can use for the measurement of the power flow in the circuit. Using the above principles and apply different types of equations, practically we can use the Hall effect in different medical applications. One of the important one is blood flow measurement. In automobiles we are using for the rotational sensing, and in space we are using as a Hall effect thruster for launching the satellite. These are the important applications. We have so many applications. Okay, please students take these two as the assignment from this lecture. Okay, and get back to the session.